Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 15. Why were logarithms developed? Focus now. Are you focused? I'm focused. All right, so why were logarithms developed? Well, there's some behind the scenes information that is not in your student edition. So I'm going to go over that first. So here it is. There's a classwork discussion, 4 minutes it says to take. How to read a table of logarithms. Okay, so for this lesson, we will pretend that we live in the time when logarithms were discovered, before there were calculators or computing machines. In this time, scientists, mechanics, merchants, and sailors needed to make calculations for both astronomical observation and navigation. Logarithms made these calculations much easier, faster, and more accurate than calculation with large numbers. In fact, noted mathematician Pierre-Simon Laplace from France around 1800 said that logarithms are an admirable artifice which, by reducing a few days the labor of many months, doubles the life of the astronomer and spares him the errors and disgust inseparable from long calculations. All right, so a typical table of common logarithms, like the table at the end of this document, has many rows of numbers arranged in 10 columns. The numbers in the table are decimals. In our table, they are given to 4 decimal places, and there are 90 rows of them. Some tables of logarithms have 900 rows. Down the left-hand side of the table are the numbers from 1.0 to 9.9. Across the top of the tables are numbers from 0 to 9. To read the table, you locate the number whose logarithm you want using the numbers down the left of the table, followed by the numbers across the top. So let's just go take a look at one page of those. And here it is. I'm on page 2, and it takes you right to the end to 9.99. Okay, here's the 9 up here. So 9.99 out 2 decimal places. Okay, and like they said, some tables go out to the 100th decimal place, and that's why there would be that many more calculations. So this was a table that they created to use to speed up the process of calculating things when they're on the water or for other purposes back in the day before we had calculators. Okay, so let's go back to the first example I'm going to give you, the only example to explain why these tables are being used. All right, so let's find the product of 3.42 times 2.47. So this is just a quick example. And if we had to do this manually, you'd go 3.42 times 2.47. And we would do long multiplication. 7 times 2 is 14, carry the 1. 7 times 4 is 28, and 1 is 29, carry the 2. 7 times 3 is 21, and 2 is 23. Bring down a 0. 4 times 2 is 8. 2 times 4 is, whoops, I'm sorry. Why did I go to the 2? 4 times 2 is 8. 4 times 4 is 16. Bring a 1 over. 4 times 3 is 12 plus 1 is 13. So as you can see, it's already tedious and there's chances of many mistakes. 2 times 2 is 4. 2 times 4 is 8. 2 times 3 is 6. And then we have to add these. 9 and 8 is 17. 6 and 4 is 10, and 4 is 14. Carry the 1. 8, 11, 13, 14. Carry the 1. And I get 6, 7, 8. 4 decimal places, 1, 2, 3, 4. So my answer is 8.4474. Okay. Okay, so now we're going to use a logarithm to find this. So all we have to do is take the log of this product. Okay, I'll put an X here for times, I guess. Okay, so the log of 3.42 times 2.47 would simplify to the log of 3.42 plus the log of 2.47, applying our product property. Okay, so now we're going to use the table. So I want the log of 3.42. So I go to my table, page 1, and I've already done this in here. And if I scroll down, you look for 3.4 down the left column, and there it is. And then you go over to the 3.42, and it meets at this location here. So with the value of the log of 3.42 is 0.5340. So let me go back. So that is going to be 0.5340 plus, now I want the log of 2.47. So I go to that table again, 2.4, go over to 7, and they come out to be, let's see, 0.3927. Okay. So 0.3927 plus 0.5340, now we add those. 7 plus 0 is 7. 2 plus 4 is 6. 9 plus 3 is 12. 5 plus 3 is 8, plus that 1 carried over is 9. And we get 0.9267. Okay, so what we're trying to think of is, what if there's more than one number that has a logarithm of 0.9267? So you suppose that there are two numbers, x and y, that satisfy the log of x equals 0.9267 and log of y equals 0.9267. Okay, so what we're saying is we're going to say, now I'm just explaining this as x equals the log of 0.9267. Okay. Or a y could equal the log of 0.9627. Okay, so what does that mean? This means that there's only one number that, actually, where am I getting? So if the log of x equals 0.9267 and log of y equals 0.9267, then that means 10 to the 0.9267 equals x. Okay, and that also means that y has to equal 10 to the 0.9267, and therefore x equals y. So there is only one solution. So what is that number? So what number is 10 to the 0.9267? So what we do then is go into our table, and we're looking for this value. We're looking for 0.9267 in the table. That'd be on page 2. 0.96 is down here. 27 is between 2 and 3. So it's either the third or fourth column. So 0.9627. 012. 0.9627 or 0.963, it's going to be between 0.9832 and 0.9836. Okay. Let's see. I apologize for that. I just caught myself in a mistake. So what I'm trying to do is find 0.9267 in this table and see what the number is. My apologies to that. You don't go to that decimal again. I was working backwards from what we were supposed to do. I'm looking for 0.9267. So 0.92586369. This is the closest one. 0.9267 is 4 10,000ths away from this one, and it's only 2 10,000ths away from this. So I want to go over now and look at this number and go up and look at this number. Okay, and so when I do that, it is 8.45. So go back to here. So that means x is approximately 8.45. And as you can see, we had 8.4474. So it's a really close approximation. And you may think this seems like a lot of work, but if you're using really big numbers, then this will actually be less tedious than multiplying really big numbers. Okay, so that is where logarithms were used back in the day before we had calculators. Okay, so let's dive into the exercises here. So keep in mind, these are all exercises. So you should pause the video after each and check to see if you did it correctly before moving on to the next. So here we go. Here is number 1. Solve the following equation. Remember to check for extraneous solutions because logarithms are only defined for positive real numbers, okay? So A is showing the log of x squared equal to the log of 49. So if you take the log of both sides, you can also get rid of the log on both sides. And since we're taking the log of something that's equal to the log of something else, those two things must be equal. In other words, if I have the log of x equal to the log of y, then x must equal y. It's that simple. So to solve this, x squared must equal 49. And to solve this, we obviously do the inverse operation of squaring. And we get x equals, and don't forget that it's plus or minus 7. Okay? Always check for extraneous solutions. If I substitute 7 in here, 7 squared is 49. If I substitute negative 7 in for x, negative 7 squared is also positive 49. So this has two solutions. There are no extraneous solutions. Okay, part B, log of x plus 1 plus log of x minus 2 equals log of 7x minus 17. The first thing we want to do is get down to 1 log on each side. So I'm going to do my product rule on the left. So this is going to be the log of x plus 1 times x minus 2 equals the log of 7x minus 17. Okay, let me fix that. I forgot my 1. Okay. So the log of x plus 1, let's fix this a little. The log of x plus 1 times x minus 2 equals the log of 7x minus 17. Simply because I had a plus sign, I multiply these. And so that's going to become the log of x squared. And it's going to be minus 2x plus x, which is minus x. 1 times negative 2 is negative 2. And that is going to equal the log of 7x minus 17. And now I have a log equal to a log, so I can just get rid of the logs now. X squared minus x minus 2 equals 7x minus 17. And if I move the 7x over here, I'm subtracting, so that would be x squared minus 8x, and add 17 to negative 2, and it's going to be plus 15 equals 0. Then we apply our zero product property to factor this. Actually, we're not getting the 0. We're factoring first, then applying the zero product property. So factors of 15 that add up to 8 are 3 and 5. They have to be the same sign, and they have to be negative because of our middle term. So it's minus 3 minus 5. And now the zero product property will give us x equals 3 or x equals 5. So then I check my values in each of these where there's a variable. So if I put a 3 here, 3 plus 1 is 4, that's fine. 3 minus 2 is 1, that's positive, that's okay as well. 7 times 3 is 21, which is more than 17. So when I subtract, I'll still be positive. X minus 3 is an answer. Plug in 5, 5 plus 1 is 6, we're good. 5 minus 2 is 3, that's good. 35 minus 17 is also going to be positive. There are two solutions, x equals 3 or x equals 5, both valid solutions. Okay, so now part C says the log of x squared plus 1 equals the log of x times x minus 2. So I'm going to do 2 steps at once here. I'm going to get rid of these logs because we only have 1 log on each side. So this has to be x squared plus 1 equals x times x minus 2. And I'm going to distribute as well in this step. That's going to give me x squared minus 2x. Okay, so the logs are gone. And I have x squared plus 1 equals x squared minus 2x. So if I subtract x squared over to the other side, it's gone. 1 equals negative 2x, and divide by negative 2, and we are done. So x is going to equal negative 1/2. So if I put a negative 1/2 in here, it's going to be positive 1/4 plus 1. That's positive, so that's okay. If I come over here, negative 1/2 times a negative 1/2 is a quarter minus a negative 1/2. So let's just show this. X times x minus 2, rather than just saying it. I'm going to substitute in a negative 1/2 for my x's. And there's a couple of ways I can do this now. I will do order of operations. So negative 1/2 minus 2, that would be negative 5/2. Okay. And a negative times a negative is positive, and that's going to give me 5/4. Okay, so that solution is a valid solution. So negative 1/2 is the solution to the equation. Okay, part D. 2 logs on one side, 1 log on the other. We need to get down to 1 log on the left. It is the product rule because of this plus sign right here. So this is going to be the log of x plus 4 times x minus 1 equals the log of 3x. Okay, and the logs will now cancel because I have a log on both sides. And that is going to become x squared minus x plus 4x is plus 3x minus 4 equals 3x. Subtract 3x from both sides, I get x squared minus 4 equals 0. Okay, add 4 to both sides, x squared equals 4. Take the square root of both sides, x equals plus or minus 2. Okay, let me show that. All righty, so take the square root of both sides, we get a positive or negative 2. So I plug in 2, 2 plus 4 is 6, that's good. 2 minus 1 is 1, that's okay. 3 times 2 is 6. So x equals 2 is a solution. I'll write that over here. So put negative 2 in, negative 2 plus 4 is 2, that's okay. Negative 2 minus 1 is negative 3, oops, we're done. Negative 1 is not a solution. My only solution is the positive 2, x equals 2. All righty, part E. We have 2 logs on one side, 1 log on the other. We need to simplify that down to 1 log, and there is a minus sign. That's the quotient rule. So it is the log of the first term, which is x squared minus x over x minus 2. Okay, that's the division, equals the log of x minus 3. Okay, and logs go bye-bye. And then we just simply have x squared minus x over x minus 2 equals x minus 3. Multiply both sides by x minus 2 to get rid of that denominator. And they're gone. X squared minus x equals, FOIL these. X times x is x squared, minus 2x minus 3x is a sum of minus 5x. Negative times negative is positive. 3 times 2 is 6. Okay, moving everything to one side. Subtract x squared from both sides. They're gone. Add 5x to negative x. I get 4x. And move the negatives or the 6 over by subtracting, and I get 4x minus 6 equals 0. And actually, I could have just left that over there. But anyhow, 4x equals 6. If I didn't move the 6, I could have had just 4x equals 6. So I made one extra step. I didn't need to, but that's okay. And now I'm going to divide both sides by 4. So x equals 6 over 4, or 3/2 or 1 1/2. So when I check this, 3/2 squared is 9/4. So that's 9 over 4. when I plug in 3/2 and I square it, minus 3/2. Okay, well, 9/4 minus equals 9/4 minus 6/4 is 3/4. So that's okay. Okay. 3/2 is 1.5. Minus 2 is -1/2. Uh-oh, we're done. No solution. Empty set. You could write it like that. You could put empty brackets for an empty set, or just simply say no solution. Okay, and last one. Okay, so let's use green this time. We have the log of x plus the log of x minus 1 plus the log of x plus 1 equals 3 log x. We have 3 logs on this side. We have 1 log on this side. We need to simplify that down to 1 on each side so they cancel. Oops. Wheel went crazy there. So this is going to be the log of x. Do I need all these parentheses? No, I'm not going to put parentheses. It's the log of x times x minus 1 times x plus 1 equals, and I'm going to do the power rule here. So it's going to be the log of x cubed. Log of x cubed. Okay, close my parentheses there. So we have a 1 log on both sides. Beautiful. Whoops. Hello. This is gone. This is gone. And now I'm just going to multiply all this out. All right. So first thing I'm going to do is multiply. Let's just get this x plus 1, x minus 1. That's a difference of squares. So that's going to be x squared minus 1 equals, I don't need parentheses on the left. It's all by itself now. Just simply x cubed. Okay. Right, x times x squared plus x minus x cancel, minus 1, difference of squares. And then when I distribute this x, I get x cubed minus x equals x cubed. Okay, subtract x cubed from both sides and I get negative x equals 0 or x equals 0. Okay, so I can't take the log of 0, no solution. Okay, cannot take the log of 0. Here's a reminder right here. If I hit log of 0. Oh, by the way, the reason I have 110 and 100 in here, going back to those tables, the tables only went up. The table we use only went to 9.99. So what if I had a number more than 1 decimal place, like 19 or 20 or 29 or 39 or 100 and something? Well, then we just remember that the log of 10 is 1. So 19 would be 1 plus what we got on the table of 9.9 and so forth. Okay, so that's why I have these up here. And now the log of 0 is going to give me an error. Okay, remember we cannot take the log of 0. So no solution. Okay, part G. We have a log, we have a log. Uh-oh, we have a negative log. What do I do with that? All right, so first of all, let's just do this. The log of x minus 4 doesn't change. Remember that a negative will flip this. So think of this as log of x. I'm going to show it. The log of x minus 2 to the negative 1. Remember, you can bring the number that's in front as a power, and that is going to change to, nothing changes over here yet. Remember that when we take something to a negative power, it is its reciprocal, 1 over x minus 2. Okay, so now we have logs on both sides that are positive and they go bye-bye. And now we have x minus 4 equals 1 over x minus 2. Multiply both sides by x minus 2 to get rid of that denominator. And we get 1 equals x squared minus 4x minus 2x more is minus 6x. Negative times a negative is positive. 4 times 2 is 8. Subtract 1 over to the other side. We get x squared minus 6x plus 7 equals 0. Factors of 7 that add up to 6. Well, 7 is prime, so it can only be 1 and 7. And I want the bigger number negative, smaller number. Oh, no, they're both negative. Timeout. Is this correct? Let's see. Yeah, it doesn't factor that way. Okay, so I wasn't wrong. I cannot take factors of 7 that add up to negative 6 because these both have to be negative, and it's prime. Negative 7 and negative 1 add up to negative 8. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Oh no, the quadratic formula. So back here, whenever I do this with my students back in the day where we were in a different course where we were learning this, I have them write a equals b equals c equals. A is my leading coefficient, it's 1. B is my linear coefficient, which is 6. And c is my constant, 7. And now I do my substitution of those values. So x equals negative. Now be careful here, negative b. Don't forget that negative plus or minus the square root of negative 6 squared minus 4ac all over 2 times a. All right. X equals 6, negative 6, plus or minus the square root of 36 minus 28. Okay, all divided by 2. So now x equals 6 plus or minus the square root of 8 all over 2. And then I do factor tree, 2 times 4, 2 times 2. So I can simplify my 8 to be 2 square root 2. So this is going to equal 6 plus or minus 2 root 2 over 2. And now those 2's will reduce and I get 3 plus or minus the square root of 2. Okay, if I go into my calculator, 3 minus the square root of 3 minus the square root of 2 equals 1.58. 1.58 minus 2 will be negative. So my negative value is going to be extraneous. So 3 plus the square root of 2, if I use my calculator, 3 plus the square root of 2 is 4.4. That's more than 4, so I won't get a negative here, and it's more than 2, so I won't get a negative here. So my answer is 3 plus the square root of 2. Okay, that is the answer, or approximated 4.4142. Okay, so that's G. That one was the most challenging so far. Number 2, how do you know if you need to use the definition of logarithm to solve an equation involving logarithms as we did in lesson 15, or if you can use the methods of this lesson? So you would say if the equation involves only logarithmic expressions, then it can be recognized to be one in the form log x equals log y, and then solve by equating x equals y. If there are constants involved, then the equation can be solved using the definition and properties of logarithms. So basically what they're saying is if you have a log on both sides, you can use this rule that we use this lesson. If it's a log of some value equal to a constant number, like the log of x plus 2 equals 8, then there's no log on the other side, so you would have to use your rules from lesson 15. All righty. Okay, this page brings us to the lesson summary. Review this lesson summary and go do your very short problem set. Is there only 3 problems? Or is there more? No, there's more. There's plenty. Okay, so there you go. Enjoy.